Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area green remainder? Quarter circle geometry. Take a moment to study the figure. Then let us uncover the two ideas that make the solution click. The target is the green remainder inside the quarter circle after the white trapezoid ABDE is removed. The two green pieces belong to one curvilinear remainder, and the answer is still hidden. The curved edge is a true 90-degree quarter circle centered at B. So the two straight edges, B across to A and B down to C, are both radii of the same length R, and the square corner of the quarter sits exactly at B. Holding on to that shared radius R is what unlocks the problem. Only two lengths are handed to us. The horizontal segment D across to E is 3, and the short gap along the base from D down to the rim point C is 1. Everything else, including the radius, we will have to earn from these two numbers. Notice where D lives. It sits on the baseline BC, and the segment DE extends straight to the right from the base. So segment DE is perpendicular to segment BC. That perpendicular is the seed of a right angle we will use in a moment. Here is the key observation. The corner E is not floating inside. It lies right on the circular arc. Every point on the arc is exactly one radius from the center, so the distance from B to E must also equal the radius R. That hands us a second radius to lean on. Let us make that radius visible. Draw the segment from B out to E. This new gold line is the radius reaching the arc, and it will become the hypotenuse of a right triangle that finally lets us solve for R. Now read triangle BDE. Since segment DE extends straight to the right from the base, the angle at D is a right angle. The legs are segment BD and segment DE, and the hypotenuse is the radius BE we drew. Perfect setup for Pythagoras. The Pythagorean theorem says the two legs squared add up to the hypotenuse squared, so segment BD squared plus segment DE squared equals segment BE squared. This is the master equation. Our whole job is now to fill in what we know. We already know one leg. Replace segment DE by its value 3, so segment DE squared is 9. The relation becomes segment BD squared plus 9 equals segment BE squared. Two unknowns remain, segment BD and segment BE, so we need one more link between them. Now walk along the base. The full radius B to C is made of two pieces, B to D plus the small gap D to C, and that gap is the given one. So segment BC equals segment BD plus 1. This is the extra link we were missing. Chain the radii together. The radius R equals segment BC, which is segment BD plus 1. And the hypotenuse segment BE also equals that same radius R. So segment BE equals segment BD plus 1, written purely in terms of the single unknown segment BD. Now feed that into the master equation. Replace segment BE by segment BD plus 1, so segment BD squared plus 9 equals the quantity segment BD plus 1, all squared. One equation, one unknown, exactly what we want. Expand the square on the right. Segment BD plus 1 squared is segment BD squared plus 2 times segment BD plus 1. Writing it out flat is what lets the segment BD squared terms line up on both sides. Put both sides side by side. Segment BD squared plus 9 equals segment BD squared plus 2, segment BD plus 1. Now the matching segment BD squared terms are begging to be canceled. Aha! The same segment BD² term appears on both sides because the hypotenuse is only 1 unit longer than segment BD. The matching squared terms cancel, leaving a linear radius equation instead of a quadratic one. Move the 1 across, so 2 segment BD equals 8, and divide by 2 to get segment BD equals 4. The base leg is finally nailed down. The radius is segment BD plus 1, which is 5. So triangle BDE has legs 4 and 3 with hypotenuse 5, the familiar 3, 4, 5 right triangle. With r equal to 5, the whole figure is now fully measured. Pause here, because we are starting a genuinely different route. Set the first solution, including segment BD equals 4 and r equals 5, aside. Return to only the original givens, segment DE equals 3 and segment DC equals 1. Then ask whether the circle itself can determine the radius. Complete the quarter circle, extend segment DE through D to F, and extend the diameter through B to G. The two full chords now cross at D. Because B is the center and segment BD is perpendicular to chord FE, the perpendicular from the center bisects the chord. Therefore, segment DF equals segment DE. The given segment DE is 3, so both horizontal chord pieces are 3. The paired tick marks make that equality visible. The vertical chord GC is a diameter, so its full length is 2r. Point D sits 1 unit above C along that diameter. Removing segment DC equals 1 leaves the other chord piece segment DG equal to 2r minus 1. Power of a point at D says that the products of the two chord pieces are equal. Watch segment DF and segment DE flash together first, then segment DC and segment DG flash together. Therefore, segment DF times segment DE equals segment DC times segment DG. This is the theorem that makes the alternate route possible. Now substitute the labels attached to the four pieces. Segment DF is 3, segment DE is 3, segment DC is 1, and segment DG is 2r minus 1. The entire geometry collapses to 3 times 3 equals 1 times the quantity 2r minus 1. Here is the second aha. 9 equals 2r minus 1, so 2r equals 10 and r equals 5. The circle has forced the same radius without using the first Pythagorean solution. Two independent routes, one local right triangle and one global circle theorem, agree on r equals 5. That agreement is both a check and a glimpse of how tightly the whole figure is connected. With radius 5, the quarter circle area is 1/4 of pi times 5 squared, which is 25 pi over 4. The white trapezoid has parallel sides 5 and 3 and height 4. Its area is 1/2 times their sum times 4, which is 16. The green remainder is the quarter circle minus trapezoid ABDE. Therefore, its area is 25 pi over 4 minus 16. Before we close, let us replay the theorem trail. Pythagoras was applied once, specifically to right triangle BDE. It connected the unknown leg segment BD. The given leg segment DE equals 3, and the radius BE. That single application opened the first route to r equals 5. Next, the center chord theorem was used once. Because segment BD is perpendicular to chord FE and starts at the center B, it bisects that chord. The theorem turned the given segment DE equals 3 into the new length segment DF equals 3. Power of a point was then applied once at D. Watch the horizontal pair segment DF and segment DE flash first, followed by the vertical pair segment DC and segment DG. Their products are equal, and substitution makes this second route reach R equals 5 independently. The quarter circle area law was used once. With radius 5, 1/4 pi r squared gives 25 pi over 4. Only the two radii and the quarter circle boundary matter in this recap. The trapezoid area law was also used once. In white trapezoid ABDE, the parallel sides are 5 and 3, and the height is 4. 1/2 times their sum times 4 gives 16. Now return to the original green remainder, geometrically unchanged. Subtract the white trapezoid area 16 from the quarter circle area 25 pi over 4. The result is 25 pi over 4 minus 16. The figure tells us which theorem fits, and each theorem does one clear job. So the final answer is 25 pi over 4 minus 16. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.